chapter is this? You don't know. Is this kinetics?
I think it might be like
No. It's the end of kinetics, yes? We did the calculate energy of activation, yes? We calculated the energy of activation? Very good.
From the graph, yeah.
We calculated energy of activation through the graph,
Yeah.
yes? We can calculate energy of activation with an equation. In the book, you might have an equation in which this K2 is on the top, K1 is on the bottom, and there's a minus here. Okay? If I switch them, what does that generate? If I switch this two, it generates a negative sign, yes? According to the log, what is it called? Log rules or something? And this minus times this minus is a positive, okay? So that equation is not different from the one in the book. It's not different from the other ones you will see. Yes or no? Okay. It is the same. And how many data points do I need to find energy of activation here? I need a temperature, yes? And I need the K that belongs to that temperature. And I need another temperature and the K that belongs to that other temperature. Okay? So in a way, how many points in a graph would that be? 2 points, yes? But when we did it graphically, we were supposed to have more than 2 points. That's why we made a graph. But if you don't have that choice of making a graph, and you have 2 data points only, this is the equation you would use. Yes? So when do you use the graph? When you have a lot of data that you can plot it. When do you use this? When you have 2 temperatures and 2 Ks.
So this formula will give you another point on the graph?
What?
This formula will give you another point on the graph that's not those 2 points?
No, this is not a graph. This is like using 2 points on the graph to make this line, which is not 2 points on the graph, it's just 2 temperatures and 2 Ks.
Can you give us an example of a problem with this equation?
Yeah, sure, maybe. Another day. I can give you one. You guys want one? What do you guys want so many problems for?
You don't trick us.
So let's say we calculated the energy of activation last time with a slope, yes? I gave you one of those. Hello?
Yes.
Somebody has not been looking at the notes, huh? Okay. So let's change this to, so calculate the energy of activation. Okay guys, what do we do here?
Rearrange the equation.
Normally, how do we calculate the energy of activation if we have a lot of numbers? We graph it. We graph what? What do we graph?
The data.
Yes, but tell me what the graph looks like.
A linear slope.
What's on the y-axis? ln of k. What's on the x-axis?
1 over t.
1 over t. And would it be a negative slope or a positive slope?
Positive.
Negative slope. Okay, and the slope of that will be equal to?
Negative energy of activation over R.
Minus EA over R. Maybe I should give you a quiz. I do not like silence. Only if you are, what is it, the dead terrorist, what's his name?
Ahmed.
Ahmed. You like the dead terrorist, don't you? You like it when he tells you to shut up? Yeah, if you guys don't know, then you're not getting the joke. Okay, well, quiz next week, okay? Monday of next week, we have a quiz. Okay? Now, I don't like the silence, okay? You have to, all right, you took a break this weekend, yes? I took one too. So, we have two data points here. We have a rate constant that belongs to this temperature, and we have another rate constant that belongs to this other temperature. We can calculate the energy of activation using this equation. K1 divided by K2, EA over R, T2 minus T1.
Yep.
Yes or no?
Mhm.
The T2 always minus T1, okay? This is always the case here. The only thing that can change is this K2 can go to the top, and this K1 to the bottom, and the minus here in the front. Other than that, that's it, okay? Normally, that's the only things that change. So I have a rate constant, and I have the temperature that belongs to that rate constant. Which one is 1, which one is 2?
One is the lowest one.
Okay, I mean, you can say this a lower temperature, and that's a higher temperature, yes?
Mhm.
So the lower temperature would be 430, and the K that belongs to that, yes? So we're gonna plug those in.
The temperature has to be in Kelvin or?
Temperature in Kelvin, yes. Why does the temperature have to be in Kelvin?
For the units to cancel with the constant.
Okay, yes, because this R is a gas constant, and this gas constant is in Kelvin. Okay, otherwise it will not cancel. Okay, so ln of K1 is 1.0 times 10 to the minus 6 inverse seconds, and divided by K2. What order is this reaction?
That's first order.
First order, very nice. You know that much. Equal to EA over R. Which one is T2?
462.
T2 is second temperature, 462.9, and this is 430.0 Kelvin. And what is a gas constant? 8.314. And how do you know that's the that's the gas constant you have to use? Because we would like units of energy in joules, yes?
Okay.
We would like units of energy in joules. That's the one you use. Can you do this math problem? Punch it in the calculator. This part here is, what did you say it was? 8.31?
That's what I did.
Okay, 8.314 joules per mole Kelvin. Okay, so we gotta solve for EA. That's gonna be difficult to do, yes? You do one number at a time and write it down. So what's this equal to? Tell me what this is equal to, only this.
Negative 3.23.
Negative
3.23.
3.23. We're looking for EA.
Right.
This minus this is equal to what?
Calculator. I need a new calculator. You can plug it all at once, right?
No, it's not good to plug it all in at once. One thing at a time.
I don't have that value.
You don't have this? You don't get this number? What number do you get? A little suspicious, but
0.03968. You have to do Wow.
What happened? We're having technical difficulties, my friends, yeah?
Yes.
I'll do it one step at a time.
Okay, guys, look. Put this stuff in the calculator. 1 divided by this minus 1 divided by that. Give me the answer, please. Before I have a nervous breakdown here. You will not be able to do this on the test.
It's negative 1.65 times 10 to the negative.
Negative?
1.65
Yeah, I got it.
times 10 to the negative.
162 something?
Times 10 to the negative fourth?
Yeah, you only have to 6.
And the units on this are on the bottom, yes? On the bottom, yes or no?
Yes, Kelvin.
Okay. So obviously, the Kelvin is on the bottom, this is on the bottom of the bottom, so that means it's on the top. Those two cancel out. Okay? And what I am doing now is, of course, this is not here, yes? This is separate. That's not part of that. I gotta solve for energy of activation for the mathematical wizards in the class. What do? Multiply this by the gas constant. I had already canceled the case out. Okay. And divide by that. Minus 1.65 times 10 to the minus 4, you said? Minus 4? What does that give you? Positive or negative?
Same number, yeah.
Yes, it's positive. So multiply 8.31 times that, divided by that.
160,000 joules per,
So 160,123
yeah.
joules per mole, yes? We want the energy of activation in kilojoules.
162.
So this is
You don't have the Mexican. You don't have the Mexican.
energy of activation is 160 kilojoules per mole. That's what we did before, yes? We did it graphically, and this is using how many points? 2 points only, or 2 temperatures and their 2 Ks. So let's say you had such a thing here. And I'm explaining this not because I feel like it, but because if I give it to you on the test, I don't want you to get this wrong. Let's say I ask you to find, let's say, you have this.
Maybe I'll split it wrong.
Okay, this is separate, okay? Let's say you have that. How do you find K from in there?
You would have to raise both
Rise it
sides.
to the E.
Take E and raise it to both sides of the equation.
To get rid of the ln and then.
There's really a word for that.
This is, remember, this is not a math course, yes? If you took math and you did not learn how to find this from here, you should go back and learn it, because I mean, there is no way. This is, I expect you guys to be able to calculate this on the test without me doing a problem, okay? But let's say I need to find that. Is that bothering you, yes or no? When you look at it and you want to calculate this, do you have a problem with this ln here in the front? Yes, you do, yes. You don't like it. It's not ln of k what you want, it's just k by itself. So you gotta get rid of this. How do you get rid of the ln of something?
Right.
E to the minus, e to the power, yes? If I do e to that, it's just gonna give me that same number. And I gotta do it on the other side, yes? So if I do it on the other side, I have e to the minus 3.18. And now I can find it. This number, I just multiply that by that. Okay? Yes? You're gonna have one of those on the test.
And it's gonna be a very small k.
What happened?
It's gonna be a very small k.
It's gonna be a small k, yeah. If you are taking the MCAT or you're taking the PCAT, you don't have a calculator, you gotta calculate this in your head.
What?
All the heck.
Scary, huh?
Well, it's not a joke.
It's not a joke. You think they allow you to use a calculator? They use calculators in math. I never took a math course that they let me use a calculator. That's why it's called math, yes?
How the
You
heck
can
is
do what in the
another
class?
E to
Do
that?
math in the class. If you have a scientific calculator, what are you gonna do in that class? Nothing at all? Alright. Let's do another problem.
So what am I doing?
Actually, let's do a graph first. Let's do this graph. We done this before?
Yes.
Exothermic or endothermic?
Excellent.
This is exothermic. This reaction is uncatalyzed. There is no catalyst. Maybe I shouldn't talk about this yet, yes? Yeah, I shouldn't talk about this. Let's not talk about this. Let's do a problem first. Determine molecularity write the overall reaction. Determine which is the intermediate. This is what it is. Here's a proposed mechanism for this. Step 1. This is for the destruction of ozone. You guys know ozone, yes? Hey, the positive thing about the ozone layer getting very thin is that you're gonna be able to get a suntan in a minute or two. Okay?
What's skin cancer?
Skin cancer too, but at least a suntan in 2 minutes, right? So girls don't have to struggle that much. Going to a tanning thing. So what is molecularity referring to?
The number of reactants.
Okay, molecularity is referring to the number of reactants, which could be? Hello? Unimolecular, bimolecular, or termolecular?
Yep.
I am glad they did not come to record my class today. I would have stabbed a few of you after class. So for the first one, unimolecular, bimolecular, termolecular. For the first one, here's an elementary step, yes? The first one is what? One molecule, this is called unimolecular. You gotta write down that this is the answer already, okay? That was a problem, now this is the answer. Unimolecular. Second, 1 and 2, bimolecular. What order is the first one? First order. And what order is the second one? Second order. Okay, so is the reaction first order or second order?
Overall, or?
Okay?
It's first
You can
and
determine
second.
the order of this reaction depending on something called the rate determining step. Apart from this, write it down. The rate determining step is the slowest step. Maybe we should add that to this question. The rate determining step is the slowest step. So if you are going on I-95, yes, it's a highway. Of course, girls do not go on highways, yes? And there is an old lady driving, and there is only one lane in the highway. One lane. Old lady is driving at 45. What's the maximum speed anybody else can go on that highway? Tell me.
45.
45, yes?
So she's
You can
determining
only go as
step.
fast as
The old lady.
the slowest, as the old lady, yes? So, if one of these steps is very slow, would the other one matter?
Nope.
No, the other one doesn't matter because the slow one is the one that is determining how fast the whole thing goes. So, the one that determines the rate is the one that is the slowest step. Okay? Why don't we write that here? Which is the intermediate and which step? And which step is the rate determining step? Okay, so what is the overall reaction? The overall reaction, we have to add both of these as if you were doing Hess's law. Yes, when we add both of these, this O3 and this O3 is on the left-hand side. What do they do to each other? They add to each other. They do not cancel. For something to cancel, it has to be on one side and on the other side. So these two are on the same side. They do not cancel. It is 2O3. Yes? I have something else on the left-hand side, which is this O here. It's oxygen radical, or this oxygen atom. And this oxygen atom is on the left-hand side of one. Is it on the right-hand side of anything else? Yes, it is. It's on the right-hand side here. So we can say that cancels with this. Gone. We don't have any more reactants. Okay, now we have something on the product side. Here is an oxygen, O2. And there is another oxygen on the same side. So what do they do with each other? They add to each other. And this is that equation balanced? Yes, it is. Okay, this is the overall reaction, yes? This is the overall reaction. Now, which one is an intermediate? The O is what canceled. It was made in one step and then used in a later step, okay? So, this OG is the intermediate.
Which one was canceled?
Yes, the one that is canceled is the intermediate. OG, not O2. Which one is the rate determining step?
The first one.
Okay. Step one is the rate determining step. Because
Slowest.
it is the slowest step.
Why is this? I'm not sure why.
You're not sure what one?
That it is the slowest.
The old lady.
What do you mean? You don't understand why it is the slowest there,
Yes.
or you don't understand why it's the rate determining
Why it
step?
is the slowest, or that's given.
Because I said to you
Okay.
that it was the slowest. Yeah, you gotta put this in, okay? You gotta write, next to one, you gotta put slow. Next to two, you gotta put fast. There's no way for you to know, yes? I have to tell you that. I have to tell you slow or fast.
Okay.
If I don't tell you, you cannot do the problem, you cannot imagine this.
This is like real world where it would actually happen. That's the only way, right?
Yeah, that's the only way you'll find it, but there's energy concerns with this, and that's the formation of a radical, which takes a while.
Okay.
Can the intermediate be more than one element?
It could, yes.
So it's whatever elements get crossed out?
Yes. Whatever gets crossed out, yes.
So I'm looking at this reaction. This is what happens up in the atmosphere when they talk about the hole in
Yes.
the ozone layer.
That is what happens.
But how if
Wow.
there's no other reactants? What is causing the
Because the
ozone
other
layer?
one is a catalyst. The other things are catalysts. When, huh? No, UV light, no. UV light does not destroy the ozone layer. What destroys the ozone layer is hairspray. Who invented hairspray? Girls, yes? No, there is something that catalyzes, and they are called fluorocarbons, yes? Fluorocarbons?
Okay.
What about, for example, if you in the question gave us the intermediate and the fast step, would we be able to determine the slow step?
Would you be able, you mean like,
Yeah, for example, instead of having to find the intermediate step, what if you in the question you give us the intermediate step and you give us which one of these is the fast step? Is there a way to use those two to determine which one is the slow step?
no, because this is experimental. A person has to sit down, okay, and a person has to say, okay, here's the destruction of ozone, yes? Up there, 2 ozone molecules become 3 oxygen molecules. This is ozone, and this is not ozone, yes? This stops the UV light from getting here. That's what it does, okay? That doesn't. So we need this. Why have we been destroying this? Does carbon dioxide destroy this? That is not destroyed by carbon dioxide. That is destroyed in general by radicals, okay? Freon 12. You ever heard of Freon 12? I don't want to get into this, but you guys provoked me. Freon 12. CF2, Cl2. Do you know what Freon 12 is? Guys, speak.
That's what
No,
you put in the
Freon,
AC,
Yes
no?
or no?
That's what you put in the AC?
That is what is in the air conditioning. Not anymore, right? At the beginning, this is what they put in every single air conditioner. Okay? You can drink this. It won't kill you. It won't do anything to you. Okay? But when it gets up there, this is like a catalyst for this. This creates radicals that gets this started. Okay? Of course, the mechanism that you see there does not involve this, yes? Does it? It doesn't involve this, but it gets started by these radicals, okay? That we have been putting up there for years and years. Okay, and that's what's destroying the ozone. Yes, it is in hairspray. It was. Not anymore. It was in the air conditionings, it's not anymore. Okay, now they have something else that does not react.
Do you know when they changed that? Like older cars probably still have this, or
Older air conditioning still have it, but you cannot buy it anymore. And
Okay.
the older air conditionings do not work with the new one, so
you're screwed.
if you have an old one, then somebody has to have counterfeit type of stuff,
Yeah. Okay.
you know? But it recently changed, it wasn't that long ago. How long ago was this?
I don't know.
My air conditioning, which was changed maybe 10 years ago, had the new one already, okay? But people had the old one too. They carry around little bottles of the stuff. But now the guy tells me, hey, they don't have the old one. If you have an old air conditioning, you gotta buy a new one.
Okay.
Something like that, that's what they're saying. Maybe they're making it very expensive. Okay? Have we talked about what a catalyst is?
No.
No? Why don't we talk about this?
Did a little bit, but
I did?
that it wasn't part of the reaction.
I said what a catalyst was?
I don't recall.
Okay, let's say it again, okay? Don't worry. We talked about catalysts for a long time, but not in this way that we're gonna do it now.
Okay.
Now, a catalyst does what? Definition of it. Speeds up the reaction without being consumed, yes? Now, how does it do that? Is the question we didn't talk about before. How does a catalyst speed up the reaction without being consumed?
It helps.
Lowering the activation energy is what most books say. I disagree. But it is true, but it's a lie. If you're a biologist, that's what you would say. If you're a chemist, you kind of say something else. Something maybe. Maybe not.
What's the chemist say?
So, I'm going to show you in a second. So, here's what a catalyst does, okay? A catalyst improves effective collisions. So, what does a catalyst do? A catalyst holds the molecule, so when something attacks it, it's always going to have the correct orientation. You were not trying to write all my words down, yes? Don't write all the words down. Listen with your ears and then write it down. Ready?
Mhm.
I'm going to say, but you first are going to listen. You're not going to write. Listen first. I'm going to check who's writing. What?
Then when something attacks it, make sure that it's in the right order.
Oh, okay. A catalyst improves effective collisions. You had written that already.
Yeah.
Your short-term memory is 3 words long. It's good. Improves effective collision. So, in a way, the catalyst, listen, the catalyst holds the molecules in place. So, most of the reactions have the what?
The right order.
The correct orientation. Write it down.
Okay.
And here's the biggest of all deals for a catalyst. A catalyst changes the reaction mechanism, which everyone disregards. No, don't write which everyone disregards. Right?
Catalyst changes.
The mechanism.
The reaction mechanism. And it introduces new intermediates. Now, a catalyst can also lower the energy of a system, so there is less energy involved in the step. But look here. Let's say I have A goes to B, yes? This is without a catalyst. And this requires, let's say, 100 kilojoules per mole of energy. Okay? Now, is it still A to B when you add a catalyst?
Yeah.
Yes, because it's not part of the overall reaction, yes? So, but here you added a catalyst. And here's what happens. When you add a catalyst, now this is like this. Yes or no? That's what happens. Now, what you see here, what is the difference between this and this? This one doesn't have a catalyst, and this one has a catalyst. So, when you look at it, you go, oh, the energy of activation went from here to here. So, when I add a catalyst, what happens to the energy of activation? It decreases. It is true, but it is not true. Because is this reaction the same reaction as this? No. It's not the same reaction. It's a different reaction. Do you expect it to have the same energy of activation if they're different?
No.
No, they have different energy of activation. Of course, the purpose of a catalyst is, if you add a catalyst to this, let's say you and I come up with a catalyst, and we add it to this, and instead of being 100 kilojoules per mole, it's 120. Is that a catalyst? No, so what do you say? Oh, that's not a catalyst.
It doesn't know when
You only use a catalyst or call it a catalyst if it decreases the energy of activation. So, the idea is that I do want you to know that a catalyst lowers the energy of activation from the uncatalyzed reaction. A catalyst lowers the energy of activation from the uncatalyzed reaction. Where's Ms. Rodriguez? The Musketeers don't know? Okay, so what does a catalyst do? Lower the energy of activation as compared to the uncatalyzed reaction. Now, what I need for you to understand is like for exactly the same for the saturated, unsaturated type of thing, yes?
Mhm.
This reaction here is different from this one. Okay? Since it's different, it has a different energy of activation. Here's a graph that I was going to draw at the beginning, and I noticed you were still drawing up. Let's say this is uncatalyzed. Catalyzed with a Z.
Yeah, I think so.
Yeah.
Okay, so this is what happens when you add a catalyst. When you add a catalyst, is the mechanism the same? No. Is it the same reaction? No. Is it the same overall reaction? Yes, it is the same overall reaction, but the little elementary steps are no longer the same. They're not the same. Are the bonds being broken and being made the same? No, they're not. So what happens is, this is what happens. That's what happens. A catalyst changes the mechanism and introduces new intermediates. The bottom of this thing here, this is an intermediate. That is an intermediate that the catalyst introduced. Now, the energy of activation is transition state minus reactants, yes? So look, from this place to this place, there is an energy of activation, yes? From here to here.
A different one.
Is it less than that?
Mm-hmm.
Yes, it's less. So would that occur faster with a catalyst if it's just this amount of energy? Yes.
Yeah.
And then it gets down here. This is a stable intermediate. Yes? But this one has to go another energy of activation. But look how small it is. From here to here. From here to here. That is also small. The addition of the individual energy of activations of those intermediates inside must be less than the uncatalyzed reaction for this to be an effective catalyst.
Okay.
Okay? If it's not less, then do we call it a catalyst? It's not a catalyst. You throw it away. It didn't work. So a catalyst will have to do this in order to be a catalyst. So if you have one that looks like this, how many intermediates does that have?
3.
3?
Mm-hmm.
There's one here, and one there. It's not an intermediate, that's the product. So that has 3 intermediates. How many energy of activations does this thing have?
4.
Okay, energy of activation from here to here, that's 1. Energy of activation from here to here, 2. Energy of activation from here to here, 3. Energy of activation from here to here, 4. Yes?
Okay.
Very good.
Say that again?
Huh?
Say that again? I lost it.
What do you want? Energy of activation
Yeah,
or
yeah.
intermediate?
Just say it one more time. Just repeat it.
Okay, intermediates is the bottom of the hills, yes? How many? 1, 2, 3. That doesn't count. Okay? Energy of activation from here to here is 1. From here to here is 2. From here to here, 3. From here to here, 4. Yeah.
On the test, we're gonna have a question that requires us to find out which one is the catalyst in a reaction.
No. What do you mean, which one is a
For
catalyst?
example, if you had an equation written out and you said, determine which the element in this reaction is the catalyst.
Well, a catalyst is most of the time not in. So if you take more advanced courses, maybe they do show you what the catalyst is doing. But in this class, I don't show you what the catalyst is doing, so no way.
Is the catalyst always an element added to another element? For example, in this
It
equation.
doesn't have to be, it's not an element most of the time. I mean, it could be an element, but it could be a compound too. But it is something that is added, yes.
What about heat?
No, heat
Those
is
are
not a
energy
catalyst.
observations.
What?
All those, the distances between the intermediate.
Well, the peaks are energy.
Now, heat is normally not a catalyst, my friends, okay? Because heat speeds up the reaction, yes? Hello?
Yeah.
Speeds up the reaction, but it is consumed, yes? It is used. The catalyst is most of the time something you add to it. It's a chemical. In general, this chemical is a solid, okay? Write this down. Heterogeneous versus homogeneous catalysis. Homogeneous catalysis, reactants and catalysts are on the same phase. Reactants and catalysts, same phase. Heterogeneous catalysis, reactants and catalysts are, tell me, on a different phase.
What do you mean by phase?
Liquid, solid, gas.
Okay, phase.
Phase, it's not phase, it's F-A-C-E, yes?
Yeah, that's what I
It's pH,
perfect.
P-H-A-T.
But is the catalyst destroyed in reaction?
No, man. Catalyst is not consumed.
Right, then what happens to it? Actually in the chemical.
In a mechanism, a catalyst will react, and in the process, it will be regenerated. In the process, it will go back to what it started to be.
Back on the reactant side?
Not on the reactant side, there is no reactant side. There is only catalyst and what it does, and then you have reactants and products all over the place. A catalyst is not on the reactant, it's not on the product, but it is part of the reaction with the reactants.
So as
And once
reaction
it is
occurs-
done, it goes back to whatever started with, which can now do another reaction with the reactant.
So the catalyst will continue to affect the reaction. Like you said, if it completely reacts, and then if it goes back, it'll completely react again with the catalyst taking place. Right?
Yes.
Okay.
So how much do you need if you have a catalyst in a reaction? How much of this catalyst do you need? A lot or little?
Depends on how much of the reaction you have.
It does not depend on that. How much do you need? A lot or little?
Not much.
Very little. Because a catalyst does one reaction, and then what does it do? Another one, and another one, and another one, and another
And
one.
it's not
You have to
consumed,
remove
so it
to
doesn't
get
matter.
your product to whatever you want.
What happened?
So you have to remove it at some point if you want your product to stop reacting?
No, it kind of, after some time, the catalyst decomposes. Okay? It's called I don't want to talk about it, but because it's not a topic of this class. But let's talk about a catalyst you might have. Okay? You have a catalyst in your body, let's say salivary amylase, yes?
Okay.
Yes? Where is salivary amylase at?
Your mouth.
In your mouth. That's why your mouth is called saliva, salivary, yes? Salivary
It's
amylase.
breaking down.
It breaks down carbohydrates, yes? So if you put a cracker in your mouth, what is it going to become? This cracker is going to be cut in places, and you are going to make glucose from it,
Mhm.
okay? It's gonna cut the carbohydrates from whatever long chain they are into, let's say, monomers. One carbohydrate molecule, instead of them sticking together.
Mhm.
If you put a cracker in your mouth and you wait, I don't know, chew it, and let your saliva do all the work. After some time, how is your mouth going to be? Sweet. Have you ever eaten and gone to sleep, and then you wake up and your mouth is sweet?
No.
Never happened to you? You have never noticed. because you guys have been texting all this time. But it happens all the time. Okay, but put a cracker in your mouth, wait 20 minutes with the cracker still in your mouth and the saliva, and then swallow that juice. Okay, I mean, you gotta salivate it, you gotta, taste it. Don't just swallow, you gotta taste the stuff. And it will be sweet. Okay, now when that saliva or that salivary amylase does not have carbohydrates, what does it do?
Say it again.
When there is no more carbohydrate, there is no more reactant for that catalyst to use, what do you think happens to that? You digest it, yes? First of all, it goes into your stomach. And it's protein, yes? It's made of amino acids. And the ones you have in your body too. When there is no reactant to be used, it gets cut into pieces, and then you use the amino acids to make another enzyme, or for whatever else. Whatever enzyme you're not using, it gets decomposed. That's the take-home message.
Okay.
You better try that sugar thing. As a kid, no one ever told you to do that? What, you?
But wouldn't brushing your teeth counteract that taste in the morning? I don't know.
No, not in the morning. Let's say you are at a party, yes, and you eat something and you're all messed up.
Oh, you fall asleep drunk type
You
thing?
fall asleep,
Okay, I know that feel.
but not for like a night. Not the night, not the entire night. It has to be for, let's say, 30 minutes. And then you wake up. You guys never take naps, right?
Oh, I do.
You guys are living a complete life of healthy habits, yes? Brush your teeth every time you eat. You don't eat any carbohydrates. You don't keep them in your mouth. You don't have saliva.
What was
You got
the
perfume in your mouth. All that stuff.
Garcia? What was the molecularity? You said determine the molecularity.
Molecularity of what?
Oh, was that?
Uni
Oh, that was the
molecular by
uni.
molecular.
Okay. Okay.
Okay? Alright guys, you try the cracker thing, okay? They tell kids to try that. I don't know why you haven't tried it yet. Because you're not kids? I think we're done with this chapter, yes?
Oh my God.
Are we?
I think it's enough for the test.
No, this is not enough for the test. We're gonna have another chapter and then the test. I'm gonna finish that other chapter probably next week. The week after that, you have the other test. Okay?
Okay.
We're gonna start the next chapter now.
That's chapter 15.
I don't know, chapter on equilibrium.
Thank you.
Guys, what else about a catalyst?
When you have a net ionic equation, when you cancel out the spectator ion, before you cancel out those spectator ions to make it a net ionic equation, the ones that you cancel appear on both sides of the equation. So would that suggest that there was a catalyst involved because it's on both sides of the equation?
No, because that's not an elementary step. It has to be canceling out in an elementary step. So you have to have a mechanism. If you don't have a mechanism, those are still called spectator ions. They're not catalysts. They're not intermediates. Okay, what else, guys? So tell me, in your mind, how does a catalyst work? Let's say Professor Obeso. Yes, you know Professor Obeso? He's gonna ask you about a catalyst, and you're not gonna make me look bad. Who comes complaining to me about you not knowing about a catalyst? I'm gonna change your grade. Who's taking Obeso this semester? Nobody? Nobody has the guts to say it?
It was 6 weeks, so I didn't take it.
Well, you took it last semester? He's gonna ask you, or whatever, biologist is gonna ask you, how does a catalyst work? What are you going to say? If you say to Obeso lowers the energy of activation, he's not gonna give you a lot of credit. Okay, fine, but how?
It increases the rate of
Efficiency increases.
So it holds a molecule in place, yes? So the next molecule coming in collides with it with the correct orientation all the time, yes? That's one of the things it does. What else does it do? Yeah, it might lower the energy of activation by, let's say, stabilizing one of the steps, okay? It introduces new intermediates, yes or no?
Okay.
Next chapter, equilibrium. These are equilibrium arrows. All reactions do not have a beginning and an end. Some reactions never end, okay? So if I have this from A, let's say A plus B give you C. If I put A in a flask, does it give me C? A by itself in a flask,
No.
does it give me any C?
No.
No. If I put A and B, does it give me C? Yes, because A reacts with B to produce C. These are called equilibrium arrows, yes? This is what indicates an equilibrium. Now, if I put in a flask only C, does it give me A and B? Yes, it does, because the reaction, the only thing that is needed to make A and B is C. It goes reverse. So this is forward, and this is reverse. Equilibrium is dynamic. Write it down. Equilibrium is dynamic. At equilibrium, reactions are still going forward and reverse. So when you have an equilibrium reactions, does it ever stop? No, it never stops. It goes forward, but it goes reverse. So at what point is this equilibrium point? The equilibrium point is when the rate of the forward and the reverse process is equal to each other, or are equal to each other. So at equilibrium, rate for the forward is equal to rate for the reverse. So in a way, it is going forward at the same speed as going
backward.
reverse. So, do you see any change?
No.
So you don't see changes in concentration, okay? Because if you make B or if you make C, what does that do? It makes A and B. And when you made A and B, now it goes to C. And C to A and B. You get it? Now, does that mean that the concentration of A and B and C are equal to each other?
No.
No. What that means is concentrations. That's what that means. Concentrations do not change over time. But they do change slightly, yes? In 1 second, you make C. It changes it in that second, yes? But then immediately it goes back to A and B, yes? So over time, concentrations are not changing. Here's the mathematical view of this. Let's give you another one. A. A gives you B. Let's say it's a gas. Whatever it happens to be, it doesn't matter. What is a forward rate? Tell me, what is a forward rate? What's the equation for the forward rate? Guys, rate from kinetics. Rate is equal to
K.
Concentration of the reactant, A. Let's say I put a 1 on top of it. Okay?
We're not talking about orders? Or...
Yeah, this is whatever order. It doesn't matter. And then for the reverse rate, what is it equal to? R equals to K concentration of what? Of B. Very good. Concentration of B. At equilibrium, these two numbers are the same number. So at equilibrium, what you have is K times the concentration of A is equal to K times the concentration of B. Yes or no? Does that tell you that the concentration of A is equal to the concentration of B?
No.
No, that doesn't tell you that. Does it say that? Let's
Between the two.
differentiate between these K's, okay? Let's say we're gonna call this K FWD for forward. That's the rate constant for what process? For the forward process. And let's call this rate for the reverse process. Reverse, REV. Does that mean that this KFWD is the same as this KREV? Are they the same? No, they're not the same. But the product between this rate constant and this A is equal to the product of these two. Yes or no?
Yeah.
All right, perfect. So what is this equilibrium? What is an equilibrium to you? If you are at equilibrium, what are you? Dead?
No.
You're balanced?
Very alive.
That's what you think, you're balanced? I don't think you're balanced. Yes, if you are at equilibrium, the two rates are the same. And equilibrium is a point that can be calculated. Equilibrium is a number that is reached. And after you reach that number, or that equilibrium, then what happens after that?
You stay at that number.
There is no overall change, even though the reaction is still going back and forth, yes?
How long?
Once equilibrium is reached, do you see concentration changing anymore? No concentration is changing. Yes or no? Here's how we calculate something called the equilibrium constant. So, if we're talking about an equilibrium, we're going to calculate something called equilibrium constant. And the equilibrium constant is products divided by reactants raised to the coefficient.
Wait.
Raised to coefficients. Let's say XY. Nossa, assim? Alright, so let's say we have this 2A G plus B gives you 4C plus 3D. Is this an equilibrium reaction, yes or no?
Yes.
It is an equilibrium reaction because
Dollars.
it has this. If it doesn't have that, it's not an equilibrium reaction. And if it is not an equilibrium reaction, what does it mean? That this becomes that, it gives you that. At the beginning you have that, and then at the end you have that. Here, what do you have?
Both.
You have some of this, you have some of that. Okay? And how much of this do you have depends on the equilibrium constant. So, we're going to write the equilibrium expression for this. The expression, which is called the equilibrium constant, yes? The equilibrium constant expression. So, wait a second, is the equilibrium constant a constant? No.
It should be because it's called a constant.
It's called a constant, yeah.
Well, if
The
it's at
equilibrium
equilibrium, it
constant,
shouldn't be changing.
the
Right?
equilibrium constant is a constant. Very good. It is a constant unless you change the temperature, yes? The equilibrium constant is a constant unless you change the temperature. So, here it is. The equilibrium constant is equal to products divided by reactants. Are these the products? These are the products, yes?
Yes.
So I am going to say that this product is a gas, so I am going to say the pressure of gas C raised to a power which is the fourth power. This is still a product. It is the pressure of gas D raised to the third power divided by the pressure of gas A raised to the second power divided by the pressure of gas B raised to the first power. What is that we just did there? What is that called? Equilibrium constant expression, yes? That's like the equation to calculate it. So, if I want to calculate the equilibrium constant, what type of numbers do I plug in there? When do I plug them in? Initial numbers? Are those initial numbers?
No, numbers at equilibrium.
Numbers at equilibrium. You cannot calculate the equilibrium constant unless you have them equilibrium numbers, yes? So you can only calculate this if you have equilibrium information. Yes or no?
Okay.
So if I tell you, oh, I put 5 ATMs of A and 5 ATMs of B, can you calculate the equilibrium constant? I put 5 ATMs of A in a flask, and I put 6 ATMs of B in a flask. Can I calculate the equilibrium constant? No, you can't. You can't
Still
calculate.
missing the other.
Now, you can only calculate it if what happens? If the reaction goes then forward, and then I find out what they are again. That's how you calculate.
So
Okay.
if I'm
You have to
using
have equilibrium numbers.
if I have two reactants, how do I know whether or not the reaction will be at equilibrium, or if it will just consume the entire reactant?
No, it will never consume the entire reactants. Well, it depends on the equilibrium constant. Okay? We're not there yet, okay?
No, but what I'm saying is, how do you tell apart a regular reaction from an equilibrium reaction?
Because some reactions are equilibrium reactions because you see them, and some reactions are not equilibrium reactions. I don't know how to tell you. I mean, like nitrogen combining with hydrogen is an equilibrium reaction to form ammonia. Other reactions are not. I don't know. It depends on the reaction. It's like, why am I a chemist? Kind of tough, right? I'm a chemist because I was not good at anything else. Actually, I was good at biology.
Please work.
Alright, so here's what we're gonna do. We're gonna calculate the equilibrium constant only if we have what? Equilibrium concentrations, yes? Now, liquids and solids are not included in the equilibrium expression. So let's say this is an L here. This is a liquid. Would I have this here?
Nope.
No. This would disappear for this reactant. I mean for this product. If it is a solid, would it be here? No. The only things that can be in an equilibrium expression are gases and aqueous. Things that have been dissolved in water or in whatever other solvent. So, gases and AQ. Of course, if we have things in AQ, we're not going to put the pressure, yes? We're going to put the concentration, okay? And the concentrations is brackets. And let's say I have this equilibrium constant. By the way, write this down. Equilibrium constants do not have units. Equilibrium constants do not have units. What does that mean? Hmm? It is a ratio, Tell me what it means. Tell me what the ratio means. If your boyfriend has $1 and you have $1,000, what is the ratio of money you guys have?
1 to 1,000.
1 to 1,000 or 1,000 to 1?
One.
You always go first, yes? Are you selfish? So you would say 1,000 to 1, yes or no? So the equilibrium constant here is products divided by reactants. So if that number is that large, what does it mean?
There's just more reactant than product.
There is a lot more what?
Product than reactant.
It is products on the top, reactants on the bottom, yes? For this number to be so very big, there has to be more of the products than there are of the reactants. Is that a lot more? Yeah.
Okay.
So this is so much more that we're gonna say that here, this is what we say when the equilibrium constant is very large like this. We're gonna say products predominate. Or we're gonna say reaction lies to the right. Because the right is the product side, yes? Reaction lies to the right. Or we're going to say reaction tends to go forward. Or we're going to say reaction goes forward, tends to go forward, whatever, forward. Yes or no?
Okay.
And if we have an equilibrium constant like this, what does that mean?
The inverse.
That in this
Reactants
case,
are
reactants predominate. There is a lot more reactants than there are products, yes?
Mm-hmm.
And the reaction tends to go where? To the left. Mainly reactants is what I have in the reaction mixture.
So the reaction goes reverse?
Hmm?
Reaction goes reverse?
Yes. What time is this class over?
Not for
30 or 40?
40. 40.
40. Well, them girls saying 30 over there, I guess they want to go, huh? They want to go and eat breakfast. Okay, what would you like to do? I call this manipulation of the equilibrium constant. This manipulation is mathematical manipulation. So this is what we do. Let's say A plus B give you C.
So, if the reaction predominates, it goes backward, primarily.
Alright.
So from towards the left, towards the reactant.
What happened?
You know what I'm saying, right?
There are no products and reactions. Doesn't reaction goes backwards because of the shocking reaction?
For what?
There are no products and reactions. Doesn't it go away from the product?
No. That has nothing to do with that. the Chatelier's principle is only used when you disturb the equilibrium. So when you add something to the equilibrium, that's what happens. But this is just equilibrium without touching it.
Now we're gonna
So you're right, only for the Chatelier's principle, which means you change stuff.
In high school chemistry, we had to equate all the Chatelier's principle. I got 20. I never understood that.
Okay, so here's A plus B, give you C, yes or no? And let's say that the equilibrium constant for this reaction is, let's say it's 4. You falling asleep in my class? I make you sleepy, don't I?
No, I'm tired.
Whenever you need to sleep, you call me, I'll go to your house and put you to sleep. By teaching you chemistry, of course. What I want to know is the equilibrium constant of this reaction. So I give you the equilibrium constant of 1, and then I want it of the other one, which is related to the previous one, yes?
Okay.
Yes or no?
Yes.
So the equilibrium constant for this is 4. What is it for that? I mean, what do you mean the same? Can't be the same, right?
1/5.
No, but it's not
Can't be the same. Different reactions, yes? Yes or no?
Yep.
They're related to each other. But for the mathematical wizards, yes? This one is products divided by reactants, yes? And the products here are, look here, C divided by, let's use concentration, okay? It's a gas, but it doesn't matter. Divided by A and B. Yes or no? For this one down here, it's still products divided by reactants. Yes or no? But now, tell me what the products and the reactants are. For the second one, it is A on the top, B on the top, and this is C on the bottom. For the wizards, what is the difference between these two? What are they of each other? They are reciprocal of each other. So should this be the same?
Don't know.
It should be the reciprocal of that on the top because I have switched the reactants and the products. So the equilibrium constant for this is equal to 1 divided by 4. How do you like that? Let's do another one, okay? You're going to have this on the test. 100% guaranteed. Let's do this one now. A plus B gives you C, yes? And let's say these are gases, okay? Let's put an end to this. Let's say these are gases. The equilibrium constant for this, still 4. And I do not want you to yell the answer. I want you to think about it. I want you to think about it really hard. And I want you to tell me what you think the answer is after you think, right? I want you to be very sure so it can shock you when you're wrong. Tell me, what is it? 4? You mean the same one as before? Absolutely not. That's the only thing it will never be 4. 8 is what I expect you to say. If you say 16, you're disappointing to me. I'm disappointed because you got it right. I wanted you to say 8. And once again, we don't want you to be right, right? I want you to get this wrong. Because most people will say, here's a 2, yes? So what do we do with the equilibrium constant? Multiply by 2. But that is not the case, because these coefficients are what? They are powers, that's right. So because they are powers, this here was a 1, and now this is a 2. Now I have to raise this thing to the second power. They're complaining about the carboxylic acid chapter. Again, did you send them the carboxylic acid? Oh, you did? When? Yes.
You guys can remember your tests and you're still going, right? You're still going up there.
All right. So what are they? They are exponents, yes? So, but let's relate them like we did before, yes? So what's the equilibrium constant for this here? The equilibrium constant is product divided by reactants, yes? So the pressure of that divided by the pressure of that and the pressure of this. Yes or no? Now, if I want the equilibrium constant for this, yes? It is the pressure of C, what? Raised to the second power divided by the pressure of A, the pressure of B. What is the difference? This to the second power, yes? Second and second. What is the difference between these two? How do you go from here to here? You get this one and do what to it? And you square it, yes? So this is why I want to find the equilibrium constant of this. If I multiply it by whatever number, I will raise it to that number. So I am going to get 4, raise it to that power, that is 16. I expect you on the test to still multiply by 2 or by 3 or by 4. That will be an answer choice on the test. I want you to think you're getting the problems right. Continue moving on while you're getting them all wrong. Should we go? Is it time to go, or you still, or you're excited and you want to do another problem? You're excited? Let's do another one. Okay, let's say it's still this, okay? I'm going to give you a new equation. Calculate the equilibrium constant for this. If you can't do this, you're ashamed to your family.
Relating to the first problem at the bottom.
The coefficients to this side,
Hmm?
and
It can't happen on this one, because that means there was a mistake in balancing the equation.
That's why we're 64, right?
with the coefficients from A, B, and
Yes,
think
they
so.
could, yeah.
so then how would you do it?
Same, you just look at which one of them changed by how much, to the power that
The
it
power
changed.
of the one is changed.
Then, but they should all change by the same amount.
What if they don't?
So that.
They have to.
So, but the number that will change, that will be taken into consideration.
They have to change by the same number, because their equation is balanced. One cannot change by 1/3 while the other one 3. It's just can't happen. Has to change by the same number.
But that's taking consideration the first one?
Yes, the first one. Violeta, what do you think, my friends? Huh? Hello? Okay? So, of course, I have given you here what type of numbers? Easy numbers, yes? But let's say that this would have been, let's say this would have been a 2 here, and this a 3. Can that be like that? No. If that would have been a 2, that's a 2A, this would have been then 4A, and that would have been 6A. In which case, you always look at the simplest, yes? You look at this one. There's a 1 in front of this, right? Then you look at whatever is in front of the other one that has a number in the front, and that's it. You don't have to use complicated numbers like 3 and 6. You might not know how you get from 3 to 6, yes? But this is easy, from 1 to 2 is 2. All right, so what happened here? The reaction was, hello?
Divided by 3.
It was reversed, yes? If it is reversed, what do? You find the inverse, yes? Reverse, inverse. So 1 divided by 4. And now there is a coefficient in the front. I look at C. C had what? It's not this C, right? That C had a 1 in the front, and here has a 1/3. I have to raise it to that power. I will raise it to what power? 1/3. So do that calculation, raise that to the 1/3.
So when you were doing it, you were referencing the first equation, right? Like the 8 is.
You could reference the second equation too, it's the same, but you don't reference the second equation because then it will be something like 2/3.
Alright. Since the products and the reactants are reversed. Okay.
Guys, yes or no? Let's bounce.
Is the answer 0.63?
I don't know, but 1/4 is 0.25, yes? And the cube root of that, what's the cube root of 0.25? If I knew any math, I would tell you, but I don't.
Yeah. 0.63.